All right, sorry. I had to step away for a second. So here's the idea I had for the first exercise. So let f be defined by dang it. And 0 otherwise is f integrable if so. Oops. What is the integral from 0 to 1 of f? All right, so let's say this. Yeah, let's give this like, I don't know, 10 minutes. Yeah, let's resume at 5:18. All right, hey guys. So let's go over this exercise here. This is actually not a super easy problem. Let's see. Let me sort of sketch the function a bit. So say this is 1, then it's like, okay, so we have like a point there, and then at like 1/2, we have a point there, and then like 1/3, we have a point there, and like 1/4, and 1/5, right? And so it kind of just continues like that. Right. We just get so so the function looks like this. These are all supposed to be at the same height, of course. So the question is this integrable? And I guess, well, so the answer is yes. So we claim that the integral from 0 to 1 of f equals 0. All right. So the intuition here is kind of like, first of all, like, okay, if you were to just take like the function 0 and then just create one of these like discontinuities like this and just randomly define it to be 1 at some specific point, then it should be hopefully like somewhat clear that that function would be integrable and the integral would be 0 because you know, you can basically isolate that one point with like an arbitrarily narrow interval in the partition and make the resulting sum be like arbitrarily small that way. So in this case, it's a little bit trickier. You can't just say that because like the points, there are infinitely many points where we sort of change the value from being 0 to being 1. And those points actually like cluster, they become dense around 0, right? So it's like, you know, so we've only made like a countable number of discontinuities, but we've seen examples where by creating a countable number of discontinuities, it's actually possible to turn what was originally a Riemann integrable function into a non-integrable function. And like with the example of like, you know, f equals 1 for rational x and f equals 0 for irrational x. So it's really the fact that like all of these points are actually isolated and they only like cluster around a single point, which is 0. And so basically it's like by creating a fine enough partition, you can kind of isolate the clustering point of all of these discontinuities in its own interval, and that will just like, you know, be then you'll just end up with some one specific rectangle that you know has area you know, delta or something, if you have delta as like the first interval, the width of the first interval. And then all of the rest of them are isolated, so you can create like arbitrarily small rectangles around those if you want. And so by doing that, like you can control the size of the upper sum, basically, right? And I guess another thing you can say is like, just when you look at this, you can automatically know that if the function is going to be integrable, the value has to be 0 because all the lower sums are automatically 0, right? So that's going to be the first thing we say. So first note that all the lower sums are 0. Okay. So, by, let's see, theorem 32.5, it suffices to show for any epsilon greater than 0, there exists a partition P such that U of Fp is less than epsilon, right? So how do we do that? Well, basically, so what we can do is, let's see. So how best to describe this? Here's how I think about doing this, okay? So construct P as follows. So P will be 0 epsilon over 2. And then so 1 over k minus, let's see, 1 over k minus how best to describe this? Like the minimum of so let's see, there's going to be k over 2k. So, okay, first of all, so let k be the maximum value of n such that 1 over n is greater than epsilon over 2. Okay. So then this is going to be like the minimum of 1 over k minus epsilon over 2. And, oh, actually, yeah, I don't know, whatever. 1/2 1 over k minus epsilon over 2. Doesn't matter. And then let's see, and then also 1 over 1/2 1 over k minus 1 over k plus 1. Oh, no, sorry. This should also be no. This should be epsilon over 2 over 4k. Sorry, I'll explain what I'm doing in a second. I know this is kind of weird. Epsilon over 4k, and then 1 over k plus minimum of 1/2. Oops. 1 over k minus epsilon over 2. Epsilon over 4k. And then a bunch of, basically all of these things are going to be 1 over j minus the minimum of 1/2 1 over j minus 1 over j plus 1. And then epsilon over 4k. 1 over j plus the minimum 1/2 1 over j minus 1 over j plus 1 epsilon over 4k. Okay, so the idea, okay, I mean, even, okay, this is like, I'm making this more complicated than it has to be. All you have to do is basically look at it this way. Let me illustrate what I'm trying to say. So what we're going to do is basically, we're going to start with an interval of length epsilon over 2, right? And then there's going to be like a bunch of points. And let's just say this is one. Even I know the spacing is all like messed up, but just don't worry about that. So automatically in the upper sum, there's going to be like the first term in the upper sum is just going to be epsilon over 2, right? Because there's like infinitely many points at 1 here. And then basically each of these other points, we're going to just make like a small, in fact, let me just like draw these like solid lines. So basically the game is just to like make, sorry, it should all be the same height. Oh, actually, there's like a rectangle drawing. Yes, yes, yes. Very good. So all that really needs to be said. Okay, and this one is like different because it's an endpoint, but whatever. So all that really needs to be said is, you know, so there's like, each of these is like a tk minus 1 and then like tk. So tk minus 1 and tk are chosen so that, you know, I guess I already used k in the previous thing. All right, let's say j. So that, you know, 1 over n, sum 1 over n is in tj minus 1 tj for sum n, and tj minus 1 is like less than like epsilon over 4k, where k is like the number of points outside, the number of discontinuities, right? Okay. So that way then like the upper sum is like epsilon over 2 plus like k times, or it's like less than or equal to, plus k times like 2 epsilon over 4k, right? Oh, so this is actually 2k, sorry. That's why I was using 4k before, because it's like epsilon over 4k in either direction, basically. And it's just that you have to choose, like, you just choose this radius to be, yeah, actually you can choose this radius to be like universal for all of them. So actually, yeah, there's a much easier way to like describe this. You can choose it uniformly for all of them, I guess. So yeah, it'll be like, so set like I don't know, delta equals something like the minimum of like, let's just, to be safe, on the safe side, yeah. So like 1/2 1/k minus epsilon over 2, and then also like 1/2 1/k minus 1/k plus 1. I mean, I don't know. I'm just not really thinking too hard about this. You might be able to get rid of some redundancy here, but I don't really care. And then let's see. And then also like epsilon over 4k. Something like that. Let's just, to be safe, make this also be strictly less than this. Then P will be like 0, epsilon over 2, 1/k minus delta, 1/k plus delta, 1/k minus 1 minus delta, 1/k minus 1 plus delta, right? And so on. So each of these points will be like, until you get to like 1 minus delta and then 1, I guess. 1 minus delta and then 1. Right. So each of the points, like 1/j or whatever, will be contained in its own interval, and the width of that interval is going to be forced to be like less than epsilon over 2k. Right. So then this is like, so this is actually strictly less than, and then this is like, or well, this just equals this just equals epsilon. Okay. Yeah, sorry. The convoluted, a little bit convoluted explanation, but I think the idea is actually pretty simple. To be honest, like if this were like, you know, an exam problem or something, and you kind of you basically gave like this description of it, if you were precise enough about it, okay, I mean, so you'd have to write something kind of like this. You know, if you drew a diagram and then also explained the diagram in words as precisely as you could, you know, I would be willing to accept that. Please don't just draw you know, a picture. Like never just use a picture as like a proof or anything like on an exam. There has to be some kind of explanation, but diagrams can definitely help clarify like what your thoughts are if you're struggling to articulate them purely through words, basically. Okay. But never only use a diagram. All right, anyway. So are there any questions about this? Yeah, I guess this is automatically must be less than or equal to this. So I think you can actually like eliminate, or sorry, you can eliminate this one, I think. Since, yeah, because 1/k plus 1 is less than or equal to epsilon over 2 by the choice of k. So yeah, that's kind of what it was like mentally tripping me up a little bit. So I think it's enough to just choose it this way. One interesting thing would be to like try to do this differently by using the like mesh version of the Cauchy criterion. So an interesting challenge. Given mesh of P is less than some delta, estimate U of FP in terms of delta well enough to be able to pick delta such that U of FP is less than epsilon. That would be, that's like a worthwhile thing for you guys to think about, I think, because this is actually, it's harder than it sounds, because an easy like weak way to estimate it would be like u of fp is like less than or equal to delta plus, and then it's like, let's say, you know, so some k times like k times, yeah, k times delta, I guess, where like k is the maximum of these n's such that 1 over n is greater than delta. But then k is like something like the floor of 1 over n. So this estimate, so like our upper bound becomes like u of fp is like less than or equal to delta plus the floor of, plus like, yeah, the floor, like floor of 1 over delta times delta or something like that. So this is like approximately 1. So what we're saying is like u of fp is approximately less than or equal to delta plus 1. And this is not good enough, right? Not good enough to make u of fp less than epsilon, right? Because you can't force delta, by picking delta to be small, you can't force delta, right? We can't force this to be less than epsilon because it's plus 1. So there is a better upper bound. And it has to do with like basically you have to look at if you're given delta, like if you imagine you know, making a partition where all of the intervals were like with delta, where delta is like mesh of p or something. So we have 2 delta, 3 delta, and so on. Right. The way I found this upper the way I found this upper bound was basically saying like, okay, so the worst, you know, we know like the worst case scenario is better than, you know, like all but finitely many of the discontinuities of f are contained in like the first interval, right? So all but finitely many discontinuities of f are in here, just in this one interval, right? So that's where the first delta came from. And then what I was saying is like, if there are k other discontinuities, right? So this k is measuring the number of discontinuities that are like outside of this interval, outside of the first interval. And then I was saying like, okay, the worst case scenario is like they're each like in their own interval of with delta. But actually it's better than that, because there has to be like some number like bigger than 1 of discontinuities, right? And like, so like a lot of the discontinuities end up getting like clustered in, you know, intervals for a while at least. So there's like a lot of overlap. So like this is actually too big. There's like a smaller upper estimate you can find. So it's like something like, look at like the largest k such that like 1 over k minus 1 over k plus 1 is like bigger than delta. That's actually where you should be looking. And that makes more sense, right? Because then it's like this k depends quadratically on 1 over delta, right? Or rather, sorry, yeah, delta, like, yeah. more, or rather it's like, you know, on like the square root of 1 over delta, something like that. So that way, this, you could replace this with something like an integer that's like asymptotically similar to the square root of 1 over delta instead of like just 1 over delta. And that way, this term becomes like square root of delta, and then you can force that to actually be, so this should be able to turn this into something approximately similar to the square root of delta, basically, right? And the reason I say that is because this becomes something like 1 over a quadratic, right? Because this is like k plus, this is literally just equal to 1 over k times k plus 1, right? So this is like 1 over k times k plus 1 is greater than delta. So like k times k plus 1 is less than delta, right? So like k plus 1, you know, you can replace this k with a k plus 1. It's like k plus 1 squared is less than delta. So k plus 1 is like less than, or sorry, this is 1 over delta. So then you'd have like square root of 1 over delta, something like that. So k is like less than square root of 1 over delta. So basically, yeah, you'll have like k of these intervals where, and then you'll end up with like another square root of, so I think you end up with like a 2, something like that. I don't know. Sorry, I'm getting carried away. But yeah. So you could do this with the, it's actually harder using the mesh, I would say. It's easier just to find a specific partition and use basically, yeah, 32.5 rather, basically rather 32.5 rather than 32.7. It's easier in this case, I would say. I think 32.7 is like better. It's better to use 32.7 when you know that a function is integrable rather than when you're trying to prove a function is integrable. So like, yeah. Yeah, I think when trying to prove a function is integrable, it is usually easier to use 32.5 than 32.7 when you know a function is integrable. It might be more useful to invoke 32.7. Yeah. I don't know. Anyway, any questions? Sorry, I know I ended up spending kind of a lot of the time on that. Let's see. I'll try to give you guys an exercise to do in the last 10-ish minutes here. So let's see. Yeah, how about this one? Okay. This isn't too bad. So 32.8. So exercise, sorry. 32.8, show if f is integrable on a b, then f is integrable on every interval CD, which is a subset of AB. Okay, so yeah, let's we'll resume at like 5:58, and then I'll try to run through the explanation as efficiently as I can. So yeah, I'll give you guys like 10 minutes to work to discuss it. Let me make some rooms for you guys to. Oh, hold on, my Zoom is like glitching. Yeah, let's just do that. And then I'll bring back the whiteboard here. All right, yeah. Yeah, there we go. Yep, so see you in 10 minutes. Okay, so it's this is actually relatively simple. So let's use the same kind of logic that we were just using. So, you know, we're going to use like theorem 32.5 to reduce the problem to showing that there exists a partition of CD so that the upper and lower sums of f on CD for that partition are within epsilon of each other, right? So what we can first do is invoke the integrability of f on, and in this case, it's actually easiest to just stick to like 32.5 for, or 32.5 for like the entire problem basically. So so there exists a partition P, or let's actually call it Q, just to, so that P will be the partition we choose in the end for CD. A partition of AB such that UFQ minus LFQ is less than epsilon, right? So this is by 32.5. Theorem 32.5, right? So we can find this partition Q, then set Q prime to just be Q union CD, and take P to be Q prime intersect CD. Okay, then P is a partition of CD because it is finite and includes, oops, well, it's a finite subset, right? It's a finite subset of CD containing C and D, right? And so, of course, like the labeling of the points in P is like, you know, there can be like a different labeling for the points in P than for the points in like Q prime or whatever. But it's, I think it's kind of immaterial for this discussion. So basically, so first of all, since Q is a subset of Q prime, right? We just, Q prime is just Q with at most 2 more points added to it. Then, so we have U of F Q prime is less than or equal to U of F Q, and L of F Q prime is greater than or equal to L of F Q. So since U of F Q minus L of F Q is less than epsilon, we also have U of F Q prime minus L of F Q prime is less than epsilon, right? Now, oops, note that if we set like, I don't know, Q1 to be like Q prime intersect AC, and Q2 to be like Q prime intersect DB, then Q1 is a partition of AC, and Q2 is a partition of DB, and the upper sum of f on q on p, or on q prime, sorry, the total upper sum is u of f q1 plus u f p plus u f q2. And a similar thing holds for the lower sums. So I don't have time to like write this all out in notation, but it's a pretty, like, if you just visualize what's going on here, if you just draw a sketch, you'll see exactly why this is true, right? Because literally all I'm doing is like, I added C and D to form Q prime, right? And now I'm just like splitting up the points in Q prime into like 3 different like collections. One that partitions the first subinterval of AB, one that partitions CD, which is like the middle one, and one that partitions DB. And then it's like the overall sum is just like the sum on the on AC, and then the sum on, you know, CD, and then the sum on DB, right? And the same thing is true for the lower sums. So, oh, sorry, this should be a lower sum. I don't know why I put a U there. Right. So, so U F Q prime minus L F Q prime equals like U F Q1 plus U F P plus U F Q2 minus, oops, L F Q1 plus L F P plus L F Q2, which is like, you know, U F Q1 minus L F Q1 plus U F P minus L F P plus U F Q2 minus L F Q2, right? And this is greater than or equal to 0. This is greater than or equal to 0, right? And this whole thing is less than epsilon, right? So, so U of FP minus L of FP is also less than epsilon, right? And that's what we wanted to show. Any questions? Yeah, I know like the notation is kind of complicated, but all of the basic ideas are actually, I would say, like surprisingly simple, right? I mean, the basic idea is just that it's like, if you force the error between the upper and lower sum for like the entire interval AB, right? If you force the whole error for that whole interval to be less than epsilon, then of course the error between just the pieces on CD and like between the upper and lower sums on CD are going to be less than epsilon, because the error for the whole interval between those two upper and lower sums is just the sum of these 3 errors for like the piece between A and C, the piece between C and D, and the piece between D and B. Like if you just draw a picture, you'll see that, right? Like the picture is just like, you know, here we have A, C, D, B, right? And so it's just like, you know, you have some rectangles, right? And then, you know, maybe the lower sums are like this or something, right? So, and then you have more rectangles, you know, and then like, right, so the errors, the total error on the entire interval AB is just the sum of these like differences in the rectangles, right? So the basic idea that we just described is literally just like, if the sum of all these is less than epsilon, then the ones in the middle, also add up to be less than epsilon, right? Like these are the ones that we're concerned with here. All right, anyway, so that's the idea. Like that basic idea is literally what motivated this entire argument. So, yeah. Anyway, yeah, that'll be all for today. So I'm gonna record the next lecture tonight, so it should be up by sometime tonight or tomorrow morning, and then I'll record the final lecture like tomorrow. So all of the lectures should be done by the end of this week. And I'll also post the next homework assignment tomorrow during the day. So you'll have, extra time to work on it. And yeah, and then next week we'll have 2 discussions and then a review, and then the final will be on Thursday. So, alrighty. See you guys next week. Or I have office hours tomorrow too, but yeah. All right, see you all.
Thank you.
Thank you.
Mm-hmm.